morning friends, I welcome you all for another lecture on the course Microprocessors and Microcontrollers. In today's class, I am going to discuss about a concept addressing modes supported by 80386 as well as different data types supported by 80386. In last few classes, we discussed about features of 80386, architecture of 80386, pin diagram of 80386 and a register organization of 80386. In this lecture, I was focusing on different addressing modes and data types supported by 80386 processor. So first, what is meant by an addressing mode? So addressing mode indicates the way in which data was represented in the operand field of the instruction. I repeat, the addressing mode indicates the way in which the data was represented in the instruction operand field. What are the different possible ways for representation of data in the instruction? Those ways we are called as addressing modes. If you go before some addresses based instructions, data was directly placed. In some instructions, data was represented through CPU registers. In some addressing mode based instructions, data was represented through a memory location address or a combination of all these things. So finally, what an addressing mode is, the way in which data was represented in the operand field of the instruction. So that indicates addressing mode. And 80386 processor supports total 11 different addressing modes. I repeat, 80386 processor support total 11 different addressing modes. What those 11 different addressing modes are? Number 1, immediate addressing mode. Number 2, direct addressing mode. Number 3, register addressing mode. Number 4, register indirect addressing mode. Number 5, relative addressing mode. Number 6, indexed addressing mode. Number 7, scaled indexed addressing mode. 8, base indexed addressing mode. 9, base scaled indexed addressing mode. 10, base indexed addressing mode with displacement. And 11, base scaled indexed addressing mode with a displacement. Out of these 11 different addressing modes, already everyone aware of 8 different addressing modes in 8086. Already we learned 8086 in previous classes. 8086 supports a good number of addressing modes. In that, whatever here I was discussing 11 different addressing modes, in that 8 addressing modes already supported by 8086. Additionally, 3 addressing modes newly defined in 80386. Those 3 addressing modes we call scaled indexed addressing modes. Like 7th one, that is scaled indexed addressing mode. This addressing mode newly defined in 80386. Then 9th one, that is base scaled indexed addressing mode. And then 11th one, that is a base scaled indexed addressing mode with displacement. These are 3 addressing modes newly defined in 80386. Rest of 8 addressing modes already we learn in 8086. The same addressing modes also supported by 80386 processor. So everyone remember friends, that is 80386. In this processor, newly 3 different addressing modes was defined. Those we can call as indexed addressing modes. Those are scaled indexed addressing mode, base scaled indexed addressing mode, and then base scaled indexed addressing mode with displacement. So anyhow, I will go and discuss all these 11 addressing modes one by one. First, I start with immediate addressing mode. What immediate addressing mode? In this addressing mode related instructions, the data was directly placed in the source operand field of the instruction. That means, what are the instructions which comes under this addressing mode? In all those instructions, data was directly placed in the source operand field of the instruction. Such instructions we can call as immediate addressing mode based instructions. If I consider example here is move EAX comma 1, 2, 3, 4, 5, 6, 7, 8 H. So here this is our immediate data. This is immediate data. This immediate data, which of a size is equal to how many bytes? This is 1 byte, this is a 2 byte, 3 byte, 4 byte. So this is a 4 byte number directly copied to EAX. We know that the size of this EAX is nothing but a 32 bit. That means a 4 byte register. So that directly this number copied to a destination register EAX. So this is now immediate addressing. Then coming to the second variety, direct addressing mode. This direct addressing mode instructions are like this. In this addressing mode related instructions, the address of the data was directly placed in the operand field of the instruction. So here address of a data, your data size may be either 8 bit or it may be 16 bit or it may be 32 bit. Whatever the data size is, that data address will directly place in the instruction operand field. So coming to example, move AX comma in brackets of 2050H. It means here I was mentioning an address of a data which is at 2050H. So from that location I am going to access my data of size at 16 bits that was copied to AX register. Now listen friends, here important thing is, here my destination is a 16-bit register which is AX. So in order to copy this 16-bit register, definitely I must go and access 16 bits from memory. I know that each and every location can hold only 1 byte of information. So meaning of this one is, what was the content that was present in 2050H as well as the content of 2051H. These are two locations data was moved to register X. That means based on your destination register, either we can access only one location of data from memory, or you are accessing two locations of data from memory, or you can go and access 4 locations data from memory. So it is the address of data. And one more thing is this direct addressing mode we can also call as absolute addressing mode. You remember this. Direct addressing mode is also called as absolute addressing mode. What absolute addressing mode? In this addressing mode related instructions, the address of the data was represented in the instruction operand field. The address of a data is your data size may be either 8 bit or it may be 16 bit or it may be 32 bit. So whatever the data we are accessing from the memory, that location address we represent in the instruction operand field. This is number 2. And number 3 is, whatever the address here we are mentioning, that address we consider as offset address. So what we can call, this is an offset address, or sometimes this is we can also call as effective address. What we can call effective address EACP. So for this particular instruction, effective address of a data is nothing but 2050H. Or for this instruction, the offset address of a data is nothing but 2050H. Now you remember friends, what effective address is? Simply the final offset address of a data is called effective address. So don't confuse offset address and effective address, more are same, but effective address is nothing but the final offset address of a data. So that you remember. And coming to the third addressing mode is register addressing. Sometimes this is also called as register direct addressing mode. It is what we can call register direct addressing. There are different names for this. One is a register addressing mode and another one is register direct addressing. So how it looks like? In this addressing mode related instructions, the data was represented in the operand field of the instruction through a register. That means initially the data is stored in a CPU register. That register was placed in in the operand field of the instruction. So in previous case, address of a data was placed in the instruction operand field. So that we can call as a direct addressing mode. But now, instead of writing our address of a data, first we copy our data into one of our CPU register. That register we place in operand field of the instruction. So then such instructions comes under register addressing mode or register direct addressing mode. Or I can say it in another way. It is like this. In this instruction, an instruction have both operands are registered, then such instructions also comes under register addressing mode. That means every instruction have a source operand as well as a destination operand. So once an instruction have both the source and destination operands both are registers, no doubt that instruction also comes under register addressing mode or register direct addressing mode. And here important thing is we can go and use almost all of CPU registers except some of them. In that one is an instruction pointer IP. Along with this, we didn't go and use a segment registers also to hold the data. So apart from that, we can go and use all our registers again except a flag register. So our data we can store in a register. We can use all general purpose registers, but we didn't go and use either segment registers or an instruction pointer IP and the flag register. So apart from these three different registers, we can go and use any CPU register to hold the data, and that register we can use in the instruction operand field. Then such instructions comes under this register addressing mode or register direct addressing. So that's important. So coming to example, and EAX comma EBX. The meaning of this one is do addition between the content of EAX register with EBX register. After addition, the result is again copied to EAX. So what's the meaning of this? The meaning of this one is EAX content is added to EBX content. Both are general purpose registers for 8036. And finally, the result is again goes to EAX. So that's the meaning of this. For this instruction, both operands are registered. So that this instruction comes under register addressing mode or register direct addressing mode. And coming to the fourth one, which is register indirect addressing mode. What this is, in this addressing mode related instructions, the address of the data was represented in the instruction operand field of the instruction. That means, I think so, this addressing mode is a combination of previous two. What are previous two? Previous one is a register addressing mode, and before that we discussed about direct addressing. In direct addressing mode, address of a data we represent in the instruction operand field. In a register addressing mode, first data stored in a register and then register we placed in operand field of the instruction. But now, in case of this register in direct addressing mode, what we can say is address of the data was stored in first some CPU register. That register we placed in instruction operand field. Previous case, data stored in a register, but now address of a data we stored in a register. That register we placed in instruction operand field. So coming as an example, move EAX comma in brackets of EBX. What's the meaning of this? Here for EBX there was a braces that indicates EBX should not contains the data. EBX contains address of a data. For example, EBX contains some address that is 402050H. Because EBX is nothing but a 32-bit register. It can hold an address 402050H. That means I can go and access my data from 402050H, 2051H, 2052H and 2053H. These are 4 locations data transferred to EAX. Why? Because I was accessing 4 locations. The reason is here my destination is nothing but a 32-bit register. So that's the meaning of this. Then coming to fifth one, that is a relative addressing mode. In this addressing mode related instructions, the address of the data was represented in the operand field of the instruction by the combination of a register and a displacement value. So you remember friends, this displacement we can also call as sometimes constant and sometimes we can also call offset. what we can call this is constant value or an offset value. That means in this addressing mode related instructions, we are representing operand or data address by the combination of CPU register and some displacement. Your displacement value size is either 8-bit or it may be a 16-bit or it may be a 32-bit, whatever it may be. So that displacement value is added to some of our CPU register which we are mentioned in the instruction. Then we are getting a final offset address of your data. So see here friends, my example is move EAX comma in brackets of EBX plus 2080H. So here this 2080H we can call displacement, or this we can also call constant, or this is also called offset. For this particular instruction, your address of a data is not only 2050H. Your address of a data is do addition between the register BX content, EBX content with 2080H. Now, what are the value that was present in this EBX, which is also we can call offset address, and this 2080 also we can call offset address. But here in order to find the final offset address of my source data, I definitely do addition between EBX content with a displacement value 2080H. Let you can assume friends, this EBX value is like this. EBX value is, let you can assume some 4 zeros are 3000H. EBX is a 32-bit register, so this is a 32-bit value. Now this value is added to a constant value which is 2080H. Then my final data address is 4 zeros 5080H. This final address we consider as effective address of our data. So this is the way how we are calculating effective address. Just now I already told you guys that is effective address is nothing but the final offset address of data. So that we are, I think everyone got a clarity about what effective address is. This 2080 we can call offset, and the value what was present in EBX also an offset. By adding up these two offset address, you will get final offset address of a data. That final offset address we call effective address. So that is about a relative addressing. Then coming to the sixth one, indexed addressing mode. In this addressing mode related instructions, the address of data was represented in the operand field of the instruction by the combination of index register and a displacement value. So what this is? Indexed addressing mode. If you compare this one with the previous relative addressing mode, only the difference in relative addressing mode, we can go and use any CPU register other than segment registers, instruction pointer and a flag register. But now here we clearly mentioned that, so that register always is an index register. So coming to an example, it is more clear if you go for an example, move EAX comma in brackets of ESI plus 2080H. Here also again we are going to calculate effective address of your source. In that process we are adding this constant value 2080, which we can also call as a displacement, or we can also call it as an offset to the content of index register. We know that ESI means extended source index register. So in this case, either you have to go and use either ESI or EDI. Only these are the options. You can't go and use other than these index register at this point. So that's the important was. And coming to the seventh one is Scalar indexed addressing mode. This is an addressing mode newly defined in 80386. What this is? Scaled indexed. It looks like a previous one. But only the difference is, in previous case we are adding a displacement value to index register. But now instead of that, we are multiplying index register value with some scaling factor. The scaling factor may be either 1 or 2 or 4 or 8. We can just multiply index register content with some scaling factor in order to get the final offset address of a data. That means in order to get a effective address of a data, simply we multiply source index register content or destination index register content with some scaling factor. That scaling factor may be either 1, 2, 4 or 8. These we are considered as the scaling factors of 80386. So in this case, the meaning of an instruction move AX comma in brackets of ESI star 2, that means first you have to go and calculate a final offset address of your source. In that process, simply we multiply ESI content with a scaling factor 2. Then what a final address you are getting, that we consider as effective address of our source. That location data is transferred to EAX. So that is the meaning of scaled indexed addressing mode. And coming to it, what is this? Based indexed addressing mode. In this addressing mode, related instructions, the address of a data was represented in the instruction operand field through the combination of a base register and index register. What a base register? It may be BH or it may be ABB. So these are two we are considering as base registers. So basically BX is called a base register, BP is nothing but a base pointer. That means here the offset address of your source can be split into two partitions. One partition can be holding ABX register and another partition you are holding EAS. In order to calculate the final effective address of our source, then what we have to do is you do addition between ABX value with ESI, then we are getting a final offset address that we are considering as effective address of your data. That address location data is transferred to EAX. So this is what a based indexed addressing mode. So in order to calculate here effective address we are calculating by simply doing addition between the content of ABX with the content of ESI. Then what are the final address we are getting? That we are considered as effective address. And coming to the ninth one is based scale indexed addressing mode. It looks like a previous one, but only the difference is in previous case index register value is directly added to base register value, but the now scenario changes. That is, before adding some index register value to base register value, first we multiply the index register value with some scaling factor. So what this addressing mode is? In this addressing mode, related instructions, the address of a data was represented in the operand field of the instruction by the combination of base register, index register and a scaling factor. So see here guys, an example, move EAX comma in brackets of EBX plus brackets start ESI into 4, star into 4. That means first you do this. That means first you multiply ESI value with the scaling factor 4. Then what are the value that we are getting? For example, like you can assume you may get some XX. This excess value now is added to EBX, then we are getting a final offset address of our source. That address we consider as effective address of a source. So that address data is transferred to EX. Again here EX is a 32-bit register, so we are going to access a 4 locations data continuously which are present in the memory itself. So that's the meaning of this. And next coming to 10th addressing mode, what this is? Based indexed addressing mode with displacement. So what this addressing mode is? In this addressing mode related instructions, the address of a data was represented in the instruction operand field through the combination of a base register, index register and a displacement value. Again you remember friends, what the displacement is? It may be a constant or it may be an offset. It may be offset. So here what happens is address of a data is split into 3 partitions. One partition is available in base register, another partition is available in index register, and third partition is represented directly in the instruction as a displacement value or a constant value or an offset value. So see here guys, an example, move EAX comma in brackets of EBX plus in brackets of ESI plus 1020H. So one portion of your data address is available in EBX, another portion of a data address is available in ESI, and another portion is directly placed in the instruction operand field as the displacement value here, that is 1020H. Once you are adding all these things, you may get a final offset address of a data that we are calling as effective address. So that address data is transferred to EAX. Again, here my destination is a 32-bit register, so that definitely I have to go and access a 4 locations data. So first location, what I was getting by doing of this summation, that location followed by 3 more locations. So then we are getting a 32-bit data. So that's about this 10th addressing. Coming to 11th, it is extension of previous one. What this 11th addressing mode is? Based scale indexed addressing mode with displacement. This is also newly defined in 80386. The difference between this and previous one is, previous case directly index register value is added to base register value and a displacement. But now we are first multiplying index register value with some scaling factor, thereafter only that is added to some base register as well as a displacement. So that's what here I was mentioned. In this addressing mode, related instructions, the address of a data was represented in the operand field of the instruction by the combination of base register, index register, scaling factor and then displacement. See here the example, then we have a clear cut idea, the difference between this and previous one. In previous one it is not exist, but now it is exist because this is a 2 is a scaling factor. So apart from that, everything is same as a previous addressing mode. These are the 11 different addressing modes which are supported by 80386. I hope everyone understand addressing modes concept of 80386. Next, I was shifted to what are the different data types that are supported by 80386. It is very important, friends, for your examination point of view also. 80386 supports total 17 different data types. How many data types it will support? 17 different data types that was supported by 80386. What those 17 different data types are? The first one is bit. Bit is nothing but binary digits. Its value may be 0 or it may be a 1. This is the first data type that is supported by my 80386. And number 2 is a bit field. What this bit field is? It is nothing but group of at the most 32 bits. That means bit field is nothing but a 32-bit number, or it may be a 4-byte number. So previous one is a bit, that may be binary digit 0 or 1, but now bit field is nothing but a group of at most 32 bits. That means a bit field of size is equal to 4 bytes or 32 bits. That was my second data type. Coming to third data type, what it is? Bit string. It was a string of continuous bits of maximum 4 GB the length. So what is this bit string? How many bits it may have? The maximum of 4 GB in the length. That is what a bit string is. And coming to the fourth one, signed byte. That means the number which we are representing in 2's complement form, and that number must have just only 8 bits. That we consider as a signed byte. Signed byte of a data, it is nothing but a 2's complement, number of size just 8 bits. That's it. It is a 2's complement number of size 8 bits. That's what we can call is signed byte. And next, unsigned byte. It is unsigned number. Every number is we consider as unsigned is a positive, and your number size is again just only 8 bits. That's what we can call is unsigned byte data. So previous case, the number is a 2's complement number, but now your number is an unsigned number. That means the number is a positive number itself. It may have just only 8 bits. Then that we are considered as unsigned byte. And coming to the sixth one, integer word. It is a nothing but signed 16-bit data. So signed 16-bit data in the sense, again this number we are representing in 2's complement, and that number must have only a 16 bits. So once your number is representing your 2's complement, definitely the number most significant bit plays a vital role. That indicates a sign of a number. Your number is a positive or it may be a negative. If a most significant bit of your number is a 1, no doubt that number have a negative sign. If a most significant bit of your number is a 0, no doubt that number have a sign a positive. That's the meaning of this. And coming to the next step, seventh data type is long integer. It is nothing but 32-bit signed data representing with 2's complement. So whenever you find a sign that indicates the number absolutely was representing by using only a 2's complement. So signed by, and previous case is signed word, and now we are seeing that long integer. All these are the signed numbers. The first one is 8-bit and second one is a 16-bit, and now is 32-bit. And coming to 8th one, unsigned integer word. So that is nothing but signed integer word is nothing but a 16-bit 2's complement number. But here now it is unsigned integer word. That means your 16-bit number is an unsigned number. That means your number is a positive number itself. And coming to 9th one is unsigned long integer. Again it is an unsigned number, and of a size is equivalent to 32-bit. It means here this number also absolutely it is a positive. And coming to 10th one is a signed quad word. That means word is nothing but a 16-bit, and quad word is nothing but 4 words. 4 words are nothing but 64-bit. So it is a signed 64-bit data or 4-word data. It is signed quad word. And coming to 11th one, unsigned quad word. That means previous case is signed quad word in the sense that a 64-bit number we are representing by using only 2's complement notation. But now coming to this, it is an unsigned quad word. It is here also we have a 64-bit number, but it is an unsigned number. That means your number itself is a positive number. And coming to 12th one, it is an offset. I am already told you your offset may be 8-bit or 16-bit or 32-bit, but here we clearly mentioned that a 16-bit or 32-bit displacement that references a memory location using any one of addressing modes. Like if you are observing relative addressing mode, indexed addressing mode, based indexed displacement addressing mode, then these are different addressing modes. We are focusing on offset value. That offset value we call there a displacement value, or we can call there as a constant value. So all these things we consider as an offset value. So here offset is a 16-bit or a 32-bit displacement that references a memory location using any one of addressing mode. Any one of addressing mode in the sense displays a relative addressing mode, indexed addressing mode, based indexed addressing mode with the displacement, based indexed addressing mode, based scale indexed addressing mode with the displacement. All these things case we are using a constant or which is nothing but an offset or a displacement. And coming to 13, which is nothing but a pointer. This consists of a pair of a 16-bit selector and 16 or 32-bit offset. What this is a pointer? It consists of a pair of a 16-bit selector and 16/32-bit offset. The combination of this we consider as a pointer. Next 14, a character. Character is nothing but ASCII. So an ASCII equivalent to any one of alphanumeric or a control character. So if you refer your keyboard guys, so all the keyboard have a different keys. In that we may found a different numerical keys, or you may found some special character keys, or you may found different alphabet keys. Once you are pressing any key over your keyboard, no doubt internally that keyboard will generate ASCII equivalent code. Because ASCII code we consider as alphanumeric code. So here the character is nothing but it may be an alphabet or it may be some controlling information. So once you press that particular character or a key, internally what happens is as ASCII code was generated for corresponding pressed key on your keyboard. That may be considered as your data type also. And 15th one is a strings. Generally string is nothing but a collection of characters. So here what a string is? These are the sequence of bytes or words or double words. A string may contain minimum 1 byte and maximum is 4 GB. So generally a character can be representing with a equal ASCII code. ASCII code is nothing but a 7-bit code, and generally we representing that is with 8 bits. So by adding of one more bit and it totally make it as total 8 bit. So here a string is nothing but a sequence of bytes, or it is a sequence of words, or it is a sequence of double words. A string contains a minimum of 1 byte and maximum is equal to 4 GB. And coming to 16th one, BCD. Here the BCD indicates it is an unsigned, unpacked BCD. That means decimal digits from 0 to 9 are represented by unpacked BCD. Unpacked bytes. Unpacked in the sense each and every decimal digit can be representing with a group of 8 binary bits. That's what we can call is unpacked BCD. And coming to the last one, 17th one is a packed BCD. That means in this case also each and every decimal symbol can be representing with a nebula bits. That means with the help of 4 binary bits only I can go and represent my decimal symbols, that is from 0 to 9. Those I can call as packed BCD. So this represents 2 packed BCD digits using a byte. A byte consists of 8 bits. So here that's why here what I can call is 2 packed BCD digits. That means each packed BCD digit can be representing with 4 binary bits. So for using of a byte I can go and represent 2 packed BCD digits. That's the meaning of this, friends. So I hope you understand what this data types which are supported by my 80386. So thank you for patient listening. We'll meet in our next class. In that I'll go and discuss some other important topic. Once again, thank you very much for patient listening.